Pavel Panchekha is going to talk to us. It seems to combine everything, parts of everything we've talked about today. Exact, real arithmetic, and geometric. Intriguing stuff.
All right. Yeah, great. Okay, so that's right. So I'll be talking about exact, real arithmetic. But I want to give a little bit of background of how I came to do this work and where you might apply, exact geometric computation. So I've actually been working in numerical methods for something like 5 years. A few years ago, I had this project called Herbie, which rearranges floating point expressions to have less rounding error. And I've also, for the last few years, been working on this FP Bench project, which tries to collect a bunch of common benchmarks so that we can evaluate numerical methods research on sort of a uniform collection of programs. And as I've been doing this and other numerical methods work, I've seen one theme come up a lot, which is that breakthroughs in robotics, in machine learning, in artificial intelligence are making people interested in the classics of computer science again. There's this sort of the old is new again situation. Because as people do this work, they now have to do more numerical computation. They're again interested in high-performance computing, in accuracy, in novel floating point formats, and that sort of thing. And that's kind of the genesis of this work as well. So some of my colleagues at the University of Washington got interested in 3D printing. So this is this novel manufacturing technology, and before you can 3D print some object, you first need a digital model of that object. So digital models are created in this programming language called a CAD language. So here, for example, is the core of a CAD language that my colleagues have been developing. So in this language, you can create cubes. You can scale and rotate them. That's what the affine transformations do. And there's some computational solid geometry operations that you can apply. And so just to give you a sense, if you haven't worked with CAD tools before, of how this works, we can take a square, we can make it twice the size, and then take another square and subtract it. And that gives us this L shape. So it's a very simplistic program that you might write in one of these CAD languages. Now, internally in the CAD language, the model is going to have to represent all of the edges and corners of the shape that you're producing. And those are, of course, real numbers. So every CAD program is a numerical program. And of course, that means error in your CAD interpreter means error in the physical object that you're going to end up printing. Now, these aren't just generic numerical programs. I think there's sort of three things that make geometric programs particularly interesting and different from other numerical programs, like the differential equation solvers that we've seen. So one is that in geometry, sine and cosine come up a lot. They're almost more important than even like division or multiplication, because sine and cosine come up anytime you have to do rotations, and also in other situations we need to align things. So sine and cosine are supremely important. Another thing that comes up a lot in geometry is that you want to reason about these geometric programs using geometric identities. So here's an example. If I start with a square, I can rotate it 60 degrees. And if I do that 6 times, I'll have rotated the square by 360 degrees, which should give me back the original square. But if I do this in floating point, I don't get back the original square. I get that square rotated by epsilon degrees. Also, it's not a square anymore. This might seem like it's not a big problem. It's pretty close. You might have barely noticed it fading in. But this is actually problematic if we then do further operations on the result. So for example, if I subtract this from the original square, I now have this incredibly thin triangle of about epsilon in height, but 1 in length. And as the user of a CAD tool, I then have to go through and remove these artifacts, lest the printer attempt to print these incredibly thin triangles and then waste material on them. So the fact that in floating point these identities don't hold is bad. It also means that you cannot easily reason about your geometric programs. It's hard to build abstractions that don't leak. Okay, and the final thing that comes up a lot in geometric programs is that we are often making control flow decisions based on floating point inputs. So Ava actually talked about this a bunch in her talk. And it's very difficult if you are, for example, asking whether this line intersects that triangle. You're getting a Boolean answer out based on floating point inputs. And that means error in those floating point inputs, which is always going to be present, could lead to error in your output, which means you are just taking a different control flow path. And at that point, you have a very difficult job constraining what can happen. So these are all challenges that make geometric programs hard to write, hard to execute correctly. But luckily, there are also some advantages to looking specifically at CAD and geometric programs. And that's that we have this very isolated domain. We're just building 3D models, not integrating differential equations. And that means that there's a limited set of operations we might want to apply. So for example, you could quite easily take the sine of 45 degrees. But you're unlikely to take the sine of 45 degrees, because that's just some random number. It has no physical meaning. And there's also a rich mathematical basis. I mean, geometry is literally as old as mathematics. So there's basically no topic you can't find more mathematical basis for. So to address these challenges and leverage these advantages, I've developed an exact arithmetic library, specifically tailored to geometric operations, and I'll be telling you about that today. So I'm going to start by telling you about the mathematical theory behind how it works. But I don't want this to be a very dry mathematical talk, so I'm also going to try to give some of the practical experiences that we've had using this implementation in an actual CAD. But before I get to that, let's start with the theory. So I want to start by being very clear what I mean by exact arithmetic. So by exact arithmetic, I mean that we want to support all the operations that we want, and we never want to get any rounding error. And this isn't ridiculous. So we all know, for example, in rational arithmetic, you can exactly represent fractions on a computer, because you can exactly represent integers, and then you can make pairs of them. And in rational arithmetic, we can evaluate the arithmetic operations, like here's addition, and we can also compare fractions, and we never get any rounding. There's a clear downside to rational arithmetic, which is that they don't represent any irrational numbers. It's kind of by definition. But mathematicians have a trick to get around this. So if we have a particular irrational number that we're very interested in, like the square root of 2, we can form what's called a number field. And effectively, this is like a fraction, but we have two numerators. One in front of, you can think of this as a 1 term, and one in front of a square root of 2 term. And these root 2 number fields also are closed under a variety of arithmetic operations. So for example, here when we do addition, these terms are multiplied. We get a term with coefficient 1, 2 terms with coefficient root 2, and 1 term with coefficient 2. But since 2 is a rational number, we can reorder that back, and we still have just these 2 terms up front. So this is the basic idea behind how my exact arithmetic library works as well. So let me start by telling you about how we represent numbers in my library. Then I'll talk a bit about arithmetic operations and then comparisons. So fundamentally, the data representation is this. And I don't want to be the guy that just throws a formula on the screen for you. The truth is here, but it takes a little bit of digesting, so I want to point out some of the important bits here. So first we have a denominator. So this denominator is going to be an integer, and this is like the bottom part of a fraction. And then like in that number field that we saw before, we're going to get many numerators. A0 through up to A sub n minus 1. We're going to have n of them. And then each of these numerators is going to be in front of a potentially irrational number. And these are just going to be the cosines of equally spaced angles from 0 to 90 degrees. So the first of these terms is always the cosine of 0. That's 0 times pi over 2n. And the cosine of 0 is 1. So the first of these coefficients represents just an integer, so that gives us rational numbers. And then the rest of them give us the ability to represent the cosine of various angles. And you can see that if we make n large enough, we can subdivide this angle as finely as we wish. And that means we represent any rational multiple of 90 degrees. Or sorry, any rational fraction of 90 degrees. So, okay, this representation allows us, this representation can be stored in a program quite easily. Right? This cosine term is purely symbolic. So we really only need to store d and the coefficients, with the number n being defined just by the length of this list. So this representation gives us the rational numbers, as I mentioned. That's just the terms with only one numerator. And we can also represent cosine terms in it. So, for example, here's a representation of the cosine of 30 degrees, and this is 22.5 degrees plus 45 degrees. This data representation also has this interesting property that I'm going to illustrate by first talking about how we might implement an addition like this. So, if we want to add two numbers, we may find that we have different numbers of numerators for the two of them. So since, this should be pi over 4, I'm so sorry. Since cosine of pi over 4, that's cosine of 40 degrees, that's just represent 45 degrees and 0 degrees, so that's two terms. Whereas to represent 30 degrees, we have terms for the cosine of 0, 30, and 60 degrees. So there's no immediately easy way to add these because we have coefficients that mean different things. But we have this property that we can always take a list and double or triple or multiply its length by an integer by inserting zeros. In fact, this is saying that we can take 0 plus 1 times cosine 45 degrees and make it 0 plus 0 times cosine 15 plus 0 times cosine 30 plus 1 times cosine 45 and then zeros for the others. So this kind of refinement lets us expand both of our representations to have the same number of terms, at which point we can add them. And if you have questions, feel free to ask them.
It's dividing 90 by some rational, some integer.
Yes.
90 degrees.
Yes. So we can just redivide both to represent both sets of angles that we're interested in. Okay, so that's the data representation. And now I want to tell you a bit about arithmetic operations, since I've already hinted at addition. Let's start with that. So in addition, we can refine both numbers to have the same cosine terms. And then we can, thanks to the associative and commutative laws of addition, we can just look at adding two cosine terms, one from one number, one from the other, at the same angle. So that's why this and this are both I times I over 2n. So adding these terms, we can just do a little bit of arithmetic, factor out that cosine term, and what we're left with is just doing a rational addition. So that's the addition algorithm for this data representation. But a little trickier than addition is multiplication. When we multiply two numbers, we're going to end up multiplying every cross term of cosine I pi over 2n and cosine j pi over 2n. So we need some way of representing these product terms, but our representation doesn't have a product of two different cosines. It only has some coefficient times the cosine of something. So here we can use a trigonometric identity. It happens to be the case that this is equal to that. Yeah, it is what it is. And now we have a sum of individual cosine terms. So we can reorganize those, reshuffle them to group-like terms, and then add these coefficients together. And that, again, gives us a multiplication algorithm that brings us back to the same data representation. And I should note that this same trick works for division, but I put it at the bottom of the slide because division is very complicated and I don't want to get questions about it. Any questions about the multiplication, though? Okay, great. So we can do addition and multiplication, and I swear we can do division. I'm just not going to say anything more about it. But the other thing, as I mentioned, in geometry we are frequently doing comparisons. The comparisons might be inequalities, like to see if a point is on one or the other side of a line, but they can also be equalities, like to determine if two lines are perpendicular. So let's talk about comparisons. Ideally, it would be nice if we can just compare those underlying representations to compare numbers. But unfortunately, we get some weird problems in this data representation. It looks like this. So for example, 0 can be represented as just, zeros in the numerator. But also 0 is equal to 1 minus twice cosine pi over 3, because that's 60 degrees, and the cosine of 60 degrees is 1/2. So we have this alternative representation of the number 0. And putting this more generally, a numeric equality of two numbers p and q does not necessarily imply the identity of the underlying data representations. So this was a significant challenge that threatened to sink our whole effort. So we've resolved it this way. And the resolution is that we have proven this pretty interesting theorem, that there exists some number c, such that if two numbers are equal numerically, then p times c and p times q are identical in the underlying data representation. And this is a theorem that derives from, I'll mention it in a bit. There isn't just that there exists, so I can give you concrete such constants. This is one that is easy to write on a slide, but there are more complicated ones that we use internally because they're faster to compute. So this is how we handle equality, and once we have an exact notion of equality, we can leverage that to do inequalities. So if we want to determine if one number is bigger than another, we can first check if they're equal. And if there's not, there's intervals around both that do not overlap. So that points us in the direction of interval arithmetic. So if we have two numbers x and y and we want to know which one is bigger, what we can do is we can evaluate x and y, just that whole cosine sum thing that I showed you, in a fixed point interval arithmetic. So here, for example, this might be the intervals we get using an 8-bit fixed point representation, and they'll overlap because 8 bits is not that many bits. And once they do that, we can just refine them, say using a 6-bit fixed point arithmetic and then even a 24 fixed point arithmetic. And the key property is that we're not going to keep refining these forever. Because we know that we can prove that the interval shrinks by a factor of 2 every time we increase the number of bits. And they can't keep shrinking forever to the same point because we know that these actually represent different real numbers due to that equality comparison that we just did. So termination in this process is guaranteed. And thanks to a bunch of caching, this isn't even super slow. So that's basically the theory behind how our exact arithmetic approach works. I did want to give, let's say, a shout out to the mathematics, which I've mostly been trying to ally here. So the reason our approach works is that cosines of rational angles are roots of these particular polynomials called Chebyshev polynomials. And that theorem I mentioned about there being a number C that makes the underlying representation identical is based on the factorization of that polynomial. So basically the factors of that polynomial are only other polynomials of the same sort. And then the representation that we use is sort of a standard representation of these quotient rings that you can form using these polynomials. We have sort of an interesting twist on it because our choice of n, which is how finally we divide the angle, is up to us, so we actually form what's called a module category. Anyway, I don't really want to get too deeply into the mathematics because it doesn't really seem like anyone here is really pumped about it, but feel free to talk to me afterward, and I can also point you to some papers that I didn't like reading and you might not like reading too. Okay, so that's the mathematical theory behind how it works, but one of the things that's been really exciting about this project is actually integrating this with a real CAD tool. So we've written everything I've described to you. It's about 1,300 lines of OCaml, and we use the zarith library to do the big integer arithmetic that we need to do rational arithmetic. And this is part of the reincarnate 3D printing project, which Chandra was talking about at ICFP on Monday. And to integrate this exact arithmetic into this 3D printing CAD tool, we've actually transparently, there's a sort of a mechanism to transparently swap the exact arithmetic in instead of floating point operations. So you can run the same code and choose with a compile time, or sorry, with a runtime flag, a command line flag, do you want to do floating point or exact arithmetic? So this is great if you want to run your tool more slowly but be more sure that it's correct. It's also actually great for debugging floating point code itself. So if you implement some algorithm and it doesn't work, is it because of floating point error or because you've missed a minus sign? And by switching to exact arithmetic, you can eliminate floating point error as one of the possibilities. So that's sort of roughly how where we tried to put this, and I learned a few lessons attempting to do this integration. So the first one is the importance of working incrementally and doing graceful degradation. And what I mean by that is that our underlying representation of numbers is actually this stuff I've been telling you about, which I've been calling Chebinomials in the code base, or just a pure floating point number. And the idea is that floating point number represents a fallback. If there's some unsupported operation that's done, instead of crashing the program immediately, which just would not be super polite, we instead print a warning and we fall back to using that floating point number. So if you didn't see a warning, no rounding error has happened, and the results you get are sound. And if you see a warning, send it to me, and I will change the code or add a special case or something along those lines. So this graceful degradation was super useful in telling us what we needed to add to make integrating into this CAD tool possible. And so the first thing we find we had to do is we had to add several operations that work symbolically. So maybe the simplest case is square roots. So square roots are not a supported operation. The reasons for this are mathematical and complicated, but what that means is that the number class also has a branch that is a symbolic square root. So if you take, for example, the cosine of 45 degrees, that's the square root of 2 over 2, and then you take the square root of that, there's no representation of that fourth root of 2 in terms of cosines and cosines, so that's represented symbolically. And for a square root, some operations we can support directly, like multiplication can be distributed under a square root, but other operations will print warnings and create influence, and basically we try to avoid using those functions in the code base. So square roots are not the only thing that we've had to support symbolically. Oh, yeah, I should note that square roots of rational numbers are supported. So like the square root of 7 is in fact a combination of rationals, but a combination of cosines, but not everything is. Square roots are not the only thing we've had to apply a mechanism like this to. We also have a collection of functions that are used to produce angles, the things that you call sine and cosine on. So of course pi is represented symbolically, as are arctangents. And the reason this hasn't been a huge pain, I mean, you can start seeing that there's a proliferation of these different symbolic operations, is that there's very little you have to do to angles. Like you rarely multiply two angles together, for example, because it wouldn't be physically meaningful. So there aren't that many operations we need to support, and they're also pretty segregated from lengths, these cosine terms. And I should note, these division by pi bits are because we use both degrees and radians in the code base. I didn't write it, take it up with Chandra. So we have these symbolic operations, and the symbolic operations mostly meant that we didn't have to write parts of the code that say use arctangent to replace that with whatever it is going to do. But there are some changes in the code that we did have to make. So I want to tell you about two of them. I think this first one is particularly funny. In the unit tests for this CAD tool, we frequently had floating point numbers. So for example, if you want to know if the area of a triangle function is correct, you compute the area of an equilateral triangle and check whether it's pretty close to that floating point number. The pretty close is how equality works for floats, but it isn't how we want equality to work for exact numbers. And of course, the area of a triangle isn't exactly equal to that, even if you added some more decimal places. So what we actually wanted to do was replace that with some sort of symbolic expression that it was exactly equal to. And we did this by sort of manually searching for symbolic forms of every floating point number in the code base. Using tools like Wolfram Alpha, if you give it a decimal number, it'll suggest symbolic expressions that come pretty close. We also did a brute force search over all small formulas to find those that evaluated to the correct floating point number. And you might imagine that there were false positives, but the basic idea was that if we replace all the floating point numbers with symbolic forms, then the unit test still passes in exact arithmetic as well as in floating point arithmetic. That gives us some confidence that we've probably done it right. So that was fun. Another form of code change that we had to do, this one's even hackier, is doing stuff to avoid doing square roots. So for example, to determine whether two vectors are perpendicular, you take their dot product and check if the dot product is equal to 0. So that would be dot of u and v equals 0. But for a floating point, you might not get exactly 0, you get close. And it's helpful to normalize the two vectors to have length 1 before you do that dot product, so the comparison is physically meaningful. But normalizing a vector means dividing by a square root. So that means these normalized vectors have square root terms, and then you're going to try to add them, and we don't support that. So that was really unfortunate. We were thinking of adding more symbolic operations, but then we hit upon the following trick. We replaced normalization here with what I call faux normalization. Normalization takes a vector and scales it so that it has length 1. Faux normalization scales a vector so that its length is pretty close. And in particular, it does that by replacing this denominator by just the maximum of any of the coordinates. So if you do a little bit of math, you know that that's within root 3 of length 1. And all that is, that's sufficient for the floating point code to work, and for the exact code not to use square roots. So avoiding square roots was a little bit, but this is the only really bad thing that we had. The other stuff mostly involved refactoring the code a little bit. So that's once we've done all these things, we have a CAD tool that passes all its tests, or all the tests it used to pass, with exact arithmetic, and it also has this full complement of functionality without doing any rounding error. We don't ever use these fallback floats and so on. The only major change is that it's now a lot slower. So let me tell you a little bit about that. What's actually most interesting about the performance of this exact arithmetic is that it is dependent on the number you are representing. Because all of these arithmetic operations depend on the number of numerators that we're storing on this value n. So addition and subtraction are O of n, but multiplication is O of n squared. And equality is usually O of n, but it's sometimes really bad because you have to compute that number c and then do a multiplication. So that really means that, for example, 45 degrees is really fast to compute with, but 40 degrees is a lot slower because for here n is 2, and for 40 degrees it's 18. And 44 degrees n is equal to 90, so it's a lot slower. This is a pretty weird performance model, which we've just had to live with. I mean, I don't have any answers for you here. But this has led to a few interesting changes to the code base as well. So for example, we used to search for a angle by iterating over multiples of 49.5 degrees. The idea being that you have 720 choices, like you'll find the right one. But this means that most of the angles you choose have an n of 720, which is way too much. So we replaced it to iterate in order of smallest n, and that gave us like a 1000x speedup. Okay, so some weird changes like that. We've also done a variety of additional tricks for performance. I mentioned that we use a value of c for the equality check that's better. There's also some early exiting and a lot of caching involved. And the end result of that was, it's 600 times slower than double precision. Okay, that actually, I'm not going to put that on the concluded slide, so let's make that a little smaller. Let's instead say it's competitive with arbitrary precision arithmetic. Right, so we were getting rounding errors, and to combat them, we would use MPFR to do higher precision floating point arithmetic. And 1024-bit MPFR is surprisingly not enough to always prevent rounding errors from being a problem. This method is competitive with it, it's just as fast, and it is, no rounding errors at all, ever. So that is exact real arithmetic for geometric computation. There's no rounding error. You can use it to transparently replace floating point for geometric computations, and it's fast enough to be competitive with MPFR. So I would be happy to take your questions, and you can check out both the code and the overall CAD tool at reincarnate.uwplc.org.
Can you go into some more detail about what are unsupported operations?
Yeah. So you're asking what operations are in fact supported and which ones aren't, and I've definitely been blurring that line a little bit. So for lengths, which are these cosine terms, all additions, multiplications, divisions, subtractions, comparisons, and inequalities are supported. And there aren't any error cases except division by zero. For this expanded wrapper we've built around that to handle CAD, the set of things that are supported is kind of haphazard because we add them as we see errors in the code base. So for example, square roots are a big one, so division by square roots works, but it gives you back to square root term, right? Multiplication by square roots works, but adding two square root terms does not, because we don't have any representation of that. That's not the square root of anything, and it might not be the sum of any cosines. So that's square root is basically supported in all the cases where you could represent the result as either a square root or a sum of these cosines. For the angle cases, those are a little more haphazard. So for example, if you take the arctangent of 0, it'll correctly give you 0. But I don't know if it does like cosine of arctangent of 1 gives you 45 degrees or something. So the angle ones are a little less supported, mostly because a lot of the angle operations aren't used much. And one of the goals with the integration was not to change the code that much, because it was in development and sort of coordinating multiple branches. So those are a little more haphazard, and I might get more pains to describe what exactly is and isn't supported. That said, adding more things to be supported is quite easy. You don't have to manipulate this underlying cosine stuff.
Just a question, so it's 600 times slower, but on which cases, or is there cases where it's at least comparatively equal, or does it depend on the, let's say, the model or something like that? For example,
it does depend on the model, right? And the main reason is that if your model is based around pentagons, you're going to have a lot of n equals 5. Yeah. And if it's based around 50-sided figures, there's going to be a lot of n equals 50. And n equals 50 is worse. So it does depend on the model. So the numbers I'm quoting are an average over the overall integration tests that Reincarnate has.
So, but does it depend also on the, let's say you have a very small model that's, with pentagons or whatever, and a larger one with, let's say we just have more pentagons, or we're not changing the characteristics of the comparison. Does it depend on that as well? So is it growing, or is it like comparable?
So I would say on one level, no, right? Because n is the same, and it's just a scaling applied to the numbers. On another level, the big integer operations will get more expensive if there are more bits in those arbitrary precision integers. So I suppose if you like scaled your model by a factor of 10 to the 10th, then it'd be a lot slower.
No, I meant like in terms of primitives. Let's say you have simply more pentagons, not just scale them, but simply more pentagons.
No. I mean, yeah. I mean, you can. No, yeah. I mean, the main cost is this n.
Yeah.
Right. So it's sort of there's some notion of like the fundamental angle involved in my computation, and that's what's going to be.
So mostly, it's not, let's say, triangle based or primitive based. Mostly.
Yep. That's right.
The kind of the
Exactly.
Okay.
Kind of similar question, perhaps. Have you observed that as computation progresses, you need to have more and more of these coefficients, or?
Yeah. So I think what you're maybe riffing off of is the idea that in rational arithmetic,
Yes.
usually the numerators and denominators get bigger.
Yes.
So we don't see that the number of coefficients changes. Really, the number of coefficients only changes when you're taking the sine and cosine of a new angle you haven't looked at before. So again, like if you have pentagons, I mean everything's going to be multiples of 18 degrees, and that's just the way it is. What we do find is that the numerators and denominators do get bigger over time. But in geometry, that tends to be less of a problem than in other forms of computation, because in geometry you're doing a lot of computation, the end point of which is making a comparison. And then you throw that computation branch away. Right, so you might think, like, mostly the actual coordinates don't change that much, only when you do a computation, but determining whether one thing is on one side of half plane or another, well, that's going to involve, doing a computation, doing a comparison, and throwing that value away. So in our particular use case, it's less of a problem than it is for other domains.
There's a library called CheckFun that does a numerical library built based on Chebyshev polynomials. Is that doing the same kind of thing? Do you know?
Maybe you've heard of it.
So it happens to be colleagues of mine, but I don't know what's inside it or anything. This looks really cool.
Okay.
Maybe theirs is too.
I can tell you a little bit about it. I don't think I mean, it's got the same. It's using Chebyshev polynomials, but I think that's where it's similarity. So the idea is you can represent any real valued function as a Chebyshev polynomial, because it's going to be finite. Maybe you'll have 1,000 terms to represent sine, but beyond 1,000 terms, it won't. You're not getting any better precision.
Sorry, I do in fact know it. Yeah, so it's using Chebyshev polynomials in the reals as a basis for the function space, which they're the same polynomials, but I think the similarities more or less end there. So we're using them basically as algebraic objects, and ChebFun is thinking of them mostly as analytic objects. Yeah, good question then.
I guess the last question. So this is mostly CPU based, right?
Yeah, we haven't done any. I mean, big integer arithmetic tends to be pretty memory heavy, so I can't imagine it being super happy on a GPU. I also don't know how to program GPUs. I mean, at all, but also no panel. So I mean, if you want to try to implement this, that sounds great. Okay.